Okay, so let me go over the schedule. So next Monday, we will be starting to cover a section on inference, specifically confidence intervals. So there'll be particular parts of chapters that I will be reviewing, but I'm also going to be going over what's today and start using more of on Monday, what's called StatKey. This is an online software program developed by some statisticians that we'll be using for doing some of this inference that usually is done through calculations, manual calculations. So it's going to replace a lot of the calculations that we normally do on in a regular statistics class. So I'll introduce that to you at the end of today's session. But next Monday also we'll have quiz number 7, which will cover what we covered this week, which is chapter 17, and we're covering chapter 19 today. So chapter 17 and 19. There might be some calculations, not many, but some calculations based on what we're covering today that might be on the quiz. So just make sure you have a calculator next to you when you take it. All right, so let's start sharing the screen. Chapter 19. So we've already talked about sampling a little bit in this course, but we're going to go into it a little more detail. So let's actually go to the. All right, here we go. Well, once again, we'll have some questions that we'll be considering at the beginning here. So suppose a large population, in a large population, 40% disagree with a new law that was been instituted somewhere. Suppose you took a random sample of 10 of people from this population. You expect exactly 4 of the 10 to disagree with the law. Would you be surprised if only 2 disagreed or if none disagreed? So what is your feeling about part A? You think that it would necessarily mean that 4 out of 10 in your sample would disagree? If 40% of the population disagrees? Just yell out. Let me say it another way.
I don't know if it like accurately represent the population because it might not be.
Right, I'm not really asking will it accurately represent the population. I'm just asking, would you expect exactly 4 people to disagree with the law if I took a sample of 10? Would that be necessarily the result I would get, or could I get something else?
You'd probably get something else.
Yeah, you could get something else, right? I mean, you have anywhere from 0 up to 10, right? Disagreeing with the law, and it's not totally without reason that you could get 0, right, out of the 10 who disagree with the law. Maybe all 10 disagree with it. It is possible with a sample of 10. How about with a sample of 1,000? Number one, would you expect exactly 400 to disagree with the law? No, right? I mean, you wouldn't expect necessarily. It could be any number, right? I mean, think of a sample just like, in flipping a coin or something 1,000 times. Would you get exactly 500 heads? Of course not, right? You can get a variety of answers. But with a larger sample, you're more likely to be closer to, in this case, 400 than you would be with a smaller sample, right? You'd be more likely to be closer to that 40%. So would you be surprised if you got only 20% or 200 saying it out of 1,000? Would that be surprising? Well, it would be more surprising than if you got 20% with a sample of 10, right? 2 out of 10, not so surprising. But 200 out of 1,000 when you're expecting 400 out of 1,000, that's a little surprising, right? And none, that would be highly unlikely. So here's the deal. The bigger the sample, the more the sample will approach the population value. Remember when I talked about the idea of doing an experiment like flipping a coin? that, if you flip the coin 10 times, you count the number of heads, some people will say 5, some will say 6, some will say 3 or 7. But if you flip the coin, several hundred times, then you will get, most people will get closer to 50% of heads, right? It would be closer. And the same thing with sampling. It's the same thing. If the population's 40% and we have a sample of 1,000, then most samples will be pretty close to, not exactly necessarily, but pretty close to that 400. But 200, that's not likely. 0 would be highly unlikely, almost impossible. Not if 40% of the population disagrees. So they're saying here is how does the concepts of long-run relative frequency, interpretation probability, and gambler's fallacy help you answer questions A and B? So which one of these questions, A or B, deal with the long-run relative frequency interpretation?
B.
B, yeah. The larger the sample, or the number of repetitions of an experiment, the closer your relative frequency is going to be to the actual population value. So if the population value is 40%, then we would expect the larger sample to give us a sample or give it a proportion that's pretty close, right? A good chance it's going to be pretty close to that 400. Now, how close depends on how big the sample is. Which one of these has to do with the idea of a gambler's fallacy? That's A, because the gambler's fallacy says the following. It says the gambler believes in that the relative frequency approach can be applied to small samples as well, right? So if in a small sample, if you see out of a sample of 10, if you see no one disagreeing with this new law, that's possible. It's not it's not 0 probability. It's possible that you sample 10 people and they just happen to be people who disagree with the law, or who don't disagree with the law. They all agree with the law. It is possible. Or could be all 10 people disagree with the law. But that would be highly unlikely with 1,000 people. So again, the gambler's fallacy says, if you ask somebody, you have a sample of 10 people, and you want to, what if you end up with nobody disagreeing with the law? Does that seem highly unlikely? And many people say yes. But the answer is really no. No, it's possible, right? It's not 0 chance of that happening. And so people use the idea of relative frequency. They use it with small samples, and that's where they make their mistake. All right, let's look at another example here. So the mean weight of all women in a large university is 135 pounds, standard deviation of 10 pounds. Now remember the empirical rule, right? For bell-shaped curves. Does anybody remember how many standard deviations from the mean is 95% of the data? I remember that. How many standard deviations from the mean?
2.
2, that's right. Now, standard deviation is worth 10 pounds. So what range, if I was asking you, in what range would you expect 95% of the women's weights to fall? What range would you give in this case here if these weights are bell-shaped? Well, if it's plus or minus 2 standard deviations and a standard deviation is worth 10 pounds, then we're saying 135 pounds plus or minus 20 pounds. And when we subtract 20, we get 115. When we add 20, we get 155. So we would say comfortably, we expect 95% of the women's weights to fall between 115 and 155 pounds. All right, let's look at B. If we randomly sample 10 women at this university, how close do you think their average weight would be to 135 pounds? You expect that to be in a more narrow range than the range we came up with in part A?
Well, I mean, since it was sampled randomly, it could be like a bit accurate, but it's also a pretty small sample.
All right.
So,
Mm-hmm.
I mean, there's also a chance that it might not be accurate, if that makes
True,
sense.
true. But would our range be more narrow or less narrow than the range in part A? What do you think?
Less narrow?
Less narrow. Okay. Anybody else?
Meant
Anybody
more
else?
narrow. Yeah.
More narrow.
Yeah.
Okay.
Smaller. Yeah.
Or narrower, right?
Yeah.
All right. Yes, more narrow is we would expect more narrow. And why? Because we're taking the average of 10 women, the average, as opposed to an individual. See, in part A, we're saying, what if we chose a woman that went random? Well, we expect we would expect 95% of 95% chance that a woman's weight would be between 115 and 155, right? That's what we would say. But part B is we're taking the average of 10 women's weights. So the average we would expect to be closer than part A. If we sampled 1,000 women, would we expect it to be even closer than even 10 women? And the answer is yes. We would expect it to be closer. Better estimate. We'll see why in a few minutes. Now, back in an earlier chapter, you might have even forgotten about this totally. We talked about this concept of margin of error. Again, this is for those of you who might have been following the election and the various polls. The polls would always report a proportion of people who support one candidate over another, and then they would say, give you, well, there's a margin of error, 5%, 10, whatever the number was. So the margin of error is something that we add and subtract from the result that we get to get a range of values. And typically we'll say we're 95% confident that the true value, the true population proportion, somewhere in between, inside that interval. So this is, an example here. So suppose 25% of adults believe in reincarnation. So suppose this is not a poll. Suppose this is the population percentage. It may be unknown, but let's just suppose this is true. So if 10 polls are taken, each asking a different random sample of 1,000 adults, and now we have each poll being 1,000 adults. Number one, would you expect each poll to find exactly 25% of the respondents expressing belief in reincarnation? Well, again, we would call this sampling variability, and we would say no. All right, because these are samples, right? Different people. We're not looking at all the people in the population. We're looking at a sample of 1,000 people. So would we expect exactly 25%? No. Maybe on average we would, but certainly not for that particular poll. If not, into what range would you expect the 10 sample proportions to reasonably fall? Well, we haven't really, based on this idea of margin of error, we would expect 25% plus or minus 3%. So 22% on the low side, 28% on the high side. So based on this idea of margin of error, that's what the range we would expect to find for that particular sample, somewhere in between those two values. All right, there's a good chance it would be in between those two values. All right. So what do people do when they do sampling? Well, first of all, they have a research question about the population. And then they figure out what variables they need to measure. Then they collect a sample and measure those variables, okay, which might involve answering questions. And then they use statistics to determine how close their answer is to the actual answer in the population. So they use statistics to do this, probability. But here's the deal. Everybody's going to come up with a different sample statistic, all right? Like in the previous example, we would have different answers to the sample proportion. So how do we know whether our sample proportion is good or not? It may be good, it may not be good, but we don't know. So how do we figure it out? So it says here, suppose most samples are likely to provide an answer that's within 10% of the population answer. Wouldn't we agree that we can reverse this concept and say the population there for the population answer must be within 10% of your sample value that you got, right? Yeah, it makes sense, right? If the sample value is within 10% of the population value, that sort of means that the population value is within 10% of the sample value. All right, so let's look at an example here. Maybe we'll do some examples to see where this is all leading. So suppose we have a population and we do some sort of test and determine if somebody carries a specific gene or not. And so here's a slice of this population, and inside this box are individual people. And suppose this gene is not a good gene, you know, it leads to some disease or something. So if you don't carry the gene, you got a happy face, right? And if you do carry the gene, you got an X through the box here. So I guess it's a bad thing. So, you know, we have various people with happy faces. We have various people with these boxes. So some people carry the gene, some people don't. Suppose you decide to take a sample of 25 people from this population. Suppose 4 of you do. So one person in our class takes a sample of 25, another takes another random sample of 25. So there's 4 of you do that. And these are the results that you get, right? Randomly sampling 25 people out of this population. So person number 1 does a random sample of 25 people, and they find that there are 25 of these X's, these X boxes here, which means you have the gene out of the 25 people. So your proportion of people that have the gene is 12 divided by 25, or 48%. Somebody else in the class does a random sample, 25 people, and they find that 9 of them have these X's here, have the genes. 9 divided by 25 is 36%, and so forth. So we see person number 3 found 10 people, person number 4 found 7 people, and these are the percentages. Now, the actual percentage in the population, what was it again? 40%? But notice that the samples vary, right? They vary around that 40%. Here's somebody who actually got 40%, exactly. But most people, the other 3 didn't. Some people, you know, one person had 48%, which is bigger than 40, and then there's 2 people who have below 40%. So this is called sampling variability. All right. So what we're going to do here is just come up with a rule for evaluating sample proportions in terms of how to determine if it's a good, how good is that sample proportion. So we're going to assume one of 2 things here, that we actually have an actual population with a fixed proportion who have that trait. In this case, it would be, right? I mean, either a person has the gene or doesn't have the gene. Sometimes we don't have this actual proportion in the population because the population is evolving over time. For example, you know, give an example of that, like the GDP of gross domestic product of a country, obviously it's going to evolve over time. So we don't know the true population of values because we don't know what's going to happen in the future. So how do we come up with it? Well, we do, you know, we have to do an experiment where we repeat the situation over and over again. We look at it over time. So that's what they mean by a repeatable situation, right? We come up with, that's, you know, that approaches a certain fixed probability. Number 2, the random sample selected from the population, or we randomly select a sample from the population, or we just, again, repeat an experiment over and over again and come up with a estimate. And we have to make sure that each outcome of the experiment is independent. Remember, independence is important. And then we have to have a large enough sample. Large enough sample. That's what it means here. Large enough sample. All right. So let's look at some examples of things that we could do this with. Election polling, obviously, is an example. If we wanted to estimate the proportion of voters who favor a candidate, the voters are the population units that we're going to be examining, and what are we going to be measuring? Whether they favor a candidate or don't, right? So we're just counting the number of them that favor a candidate. Television ratings is another one. We collect households with television sets. That would be our population, and we wanted to see if they are tuning into a particular TV program. That's what we're measuring. We're just counting the number of people. Population, we could be, there's a manufacturer, maybe soft drinks. They want to see if a new mixture of ingredients is better than an old mixture, so they'll do a survey. And what's the population? The consumers who use this sort of soft drink. And what are we measuring? Whether they prefer the new formula to the old formula. So in every case here, what are we doing? We're counting the number of people who prefer one thing over another, and then we do a proportion. We take that count, divide up the total number of people we asked, and that's the proportion of the sample that prefers that thing, whatever it might be. Now, what we do in statistics or in research is, or whoever's doing the research, is they take one sample, right? They don't do multiple samples. They take one sample, and they come up with a sample proportion. If it's a consumer products company and they make soft drinks, they say, all right, how many people out of all those polled like this new formula that we've created? And then we count the number of people like it, we divide by the number of people we asked. That's our proportion. But you can picture multiple people doing the same research, right? And coming up with different proportions, different sample proportions. Let's assume that we use a computer or something, and we could list all of those possible answers, possible proportions. All right. The question is, what would be the mean of all those proportions, and what would be the standard deviation? So now what we're looking at is a list of all possible samples of a certain size with their proportions, sample proportions. We have a list of them. Right? Our computer generated this list. One of those samples is the one we actually generated, one we actually had, but there's all other possible samples too of that size. So the mean, here's what's very interesting, that the mean of all those sample proportions, if we averaged all of them, it will be mathematically true to be equal to the proportion for the whole population. So if we were able to list all of the possible sample proportions and took the average of all of them, it would be equal to the population proportion. What is the standard deviation? Well, we need to use this formula here. It's the square root of what? The true proportion. And now you might say, well, what if I don't know the true proportion? Well, you might come up with an estimate for it. But you would put the proportion, the estimated proportion here, and then you would have it as a decimal between 0 and 1. And then 1 minus that true proportion would be also between 0 and 1. You would multiply those two numbers, divide it by the size of your sample, 25, 100, 1,000, whatever number of people are in your sample, and take the square root of that ratio. And that will give you your standard deviation. It's a standard deviation of what? It's the standard deviation of a curve that represents the list of all these possible sample proportions. And according to this, it would be approximately bell-shaped. Okay, the curve is going to be approximately bell-shaped. The mean of the curve would be the mean of the population proportion, because the mean of all those sample proportions is equal to the population proportion, and the standard deviation would be the result of this formula. So here's an example of how it works. Suppose 40% of all voters in the US favor candidate X. Now, obviously we don't know that, but suppose that somebody estimates that to be true. So pollsters take a sample of 2,400 people. What sample proportion would be expected to favor candidate X? Now, this question is not asking for one number. It's asking for a range of numbers. That's what it's asking for. All right, just know that. Because you don't know what sample proportion you're going to get, right? You can get some number below 40%. You can get some number above 40%. But what we're going to do now is we're going to come up with a calculation that will determine our estimated range of proportions. So we have our mean as 40%. Remember, 40% is the mean of the population, but it's also the mean of the list of all possible sample proportions. We listed them all. For every sample you could possibly imagine, the mean or average of all those proportions would be 40%. So we're going to plug into that previous formula. That's this formula here. We're going to plug it in. 0.4 times 1 minus 0.4 divided by the sample size of 2,400. And we get the answer as 0.01. 0.01 is 1%. If you multiply that by 100, that's 1%. So the standard deviation is 1%. Okay, if we express it as a percentage as opposed to decimal. So we can answer this question by saying the following, using the empirical rule. Because we are able to use the normal, the bell-shaped curve for this, okay, the bell-shaped curve we can use. You can say the following. There's 68% chance that the proportion for the sample that we choose, that is the 2,400 people that we choose, the proportion of people who favor candidate X, there's a 68% chance that it's between 39% and 41%. Now, how did we come up with that? Well, remember, the empirical rule says the mean plus or minus 1 standard deviation is 68%. Well, the mean is 40%. The standard deviation is 1%. So 40 minus 1 is 39. 40 plus 1 is 41. 68% chance that the sample that you choose will have a sample proportion between 39% and 41%. The empirical rule also says that there's a 95% chance that your sample proportion will be between plus or minus 2 standard deviations from the mean. Now, 1 standard deviation is worth 1%. 2 standard deviations is worth 2%. 40 minus 2 is 38. 40 plus 2 is 42. So we would expect 95% chance that the sample that you choose at random, that you particularly choose at random, is between 38% and 42%. And then we would say with 99.7%, that's what they mean by almost certain, 99.7%, that you're going to be within plus or minus 3 standard deviations from the mean. Well, 1 standard deviation is 1%, 3 standard deviations is 3%. 40 minus 3 is 37, 40 plus 3 is 43. We would be almost certain that the sample proportion is between 37% and 43%. And that's the answer to the question. We have to give a range of values, not just one value, because we don't know what that one value is going to be. But we can almost be certain that whatever we choose is going to be between 37 and 43%. Now, I'm going to propose a question to you. Suppose you do the sample and you find the answer is 60%. Suppose you did a poll and it's 60%. And suppose this 40% figure came from some company that does this sort of thing. You know, they estimate population stuff, and they come up with this 40% number for the whole population. If you got, through your poll of 2,400 people, you got an answer 60%. And if it is true that 40% of all voters favor candidate X, it's almost certain, with almost 100% certainty, that your sample should be between 37 and 43, and yet you got 60%. Would you not agree? Wouldn't that cast doubt on the original assumption that 40% of all voters favor candidate X? Right? Because according to this, it would be practically zero chance that your sample proportion would be 60%. It's just so far away from these numbers. So that would cast doubt on this original 40% figure. So I'm giving you sort of a heads up of where this is all leading to. This is what's called hypothesis testing. Somebody comes up with a hypothesis. Then you do sampling, and then you say, all right, how likely is it that I got my sample results and it's just normal variation around the mean that's being proposed? And if it's considered extremely unlikely, then you're going to say, all right, that assumption, like this 40% assumption, seems to be incorrect. That's called hypothesis testing. Pretty cool how it works. And it works without knowing what the actual population value is, which is really pretty remarkable. Now, how about if we, instead of dealing with proportions, because sometimes that's what we do, right? We have categories and we count the number of people in each category. What if we're actually measuring something? For example, we're measuring a person's weight loss from attending a weight loss clinic for 10 weeks, okay? So you're attending this weight loss clinic, and then suppose, unknown to us, the population mean weight loss from this weight loss clinic, that would include not just people who've taken this program in the past, but people are going to be taking it in the future. So we don't really know. But suppose the answer is 8 pounds. Suppose that's the average weight loss for everybody in the population, and it has a standard deviation of 5 pounds. Suppose we know weight losses are approximately bell-shaped. Okay. Now, if it's approximately bell-shaped, that means we can use the empirical rule. So we can say that if we choose somebody at random, there's a 95% chance that their weight will fall, that their weight loss will fall between -2 and +18. Now, where did they come up with this? Well, 95% is plus or minus 2 standard deviations. A standard deviation is worth 5 pounds, so 2 standard deviations is 10 pounds. 8 minus 10 is -2. 8 plus 10 is 18. And by the way, if a weight loss of -2 means you've actually gained weight. I don't know if I were you, but I would be kind of angry if I took a weight loss program for 10 weeks and I actually gained weight. But it says here it's possible, right? With these numbers here, that it could be somebody or some people who lose or gain weight instead of lose weight. But there's a 95% chance that if you do gain weight, it's not going to be more than 2 pounds. Suppose you took random samples of 25 people from this population, and 4 of you did, and so here are the results for the 4 of you, the weight losses. Okay. So for sample number 1, the mean weight loss is 8.32 pounds. This is its standard deviation. Sample 2, this is the mean weight loss. Sample 3 and sample 4. As you can see, sampling variability, right? Now they're all right around 8, not too far from 8. You know, we don't see 2 pounds or 20 pounds in here. So it's reasonably close. But this is the result of what? 25, the sample size of 25. Okay. Sampling variability. Now, are any of these good? Well, certainly the ones that are around 8 pounds are good, right? They're pretty close. 6.76 pounds, not as good, but not far away. So how do we use all of this? How do we come up with this? So here is the conditions for the rule for sample means. Now, we had a rule for sample proportions before. Now we're measuring something like weight loss. And here's the deal. If the population from which we are choosing the sample is bell-shaped, in other words, if what we're measuring is bell-shaped, then it doesn't matter how large the sample that we choose. It could be any size. And our sampling, our distribution of means, I'll tell you what that means in a minute. This distribution of sample means will be bell-shaped also. But it says here that if the population of these measurements is not bell-shaped, possible it's not bell-shaped, then you need a minimum sample size. Typically, people choose 30. Could be bigger, but all the textbooks say 30. So we need a sample size of 30 to ensure that the curve, the frequency curve for our list of samples with sample means is approximately normal. All right, so let's actually do let's look at some examples here. These examples, by the way, are just looking at the population and what we're measuring. So we know that in the case of the weight loss, the population are all the current and potential clients of the weight loss clinic, right? That's the population. Potential meaning future clients. And the measurement, of course, is how much do they lose in those 10 weeks. Obviously, there are other examples. Here's another example here. This is the average age at which a left-handed adult dies. I don't know why anybody wants to know that, but that's what. And we're assuming they've lived to at least age 50. They're saying here the ages at death are not bell-shaped, so we need at least 30 such people in our sample. All right. What's the population? All left-handed people. And what's being measured? Their age at death. All right. So again, what we're going to be doing is we're going to now obviously in our own research, we're going to pick one sample of a certain size. When we say size, what are we referring to? We're referring to the number of people in our sample. But if we could list all possible samples of that sample size, and whatever we're measuring, we find the mean or average of that measurement for each one of those samples, then the frequency distribution of those means would be approximately bell-shaped according to these rules here. These rules. If the population is bell-shaped, it doesn't matter how large a sample is. This curve will be bell-shaped. But if the population is not bell-shaped, then we need at least 30 people in our sample. Okay. Regardless, the mean for this curve is going to be equal to the mean of all those means. That sounds funny, but the list of all the means for all those samples, if we took the mean or average of all of them, it would be equal to the mean for the whole population. So the mean is going to be the mean for the whole population, and the standard deviation is going to be the population standard deviation divided by the square root of the size of the sample. How many people are in the sample? For example, in the weight loss situation, suppose weight loss is bell-shaped, all right, with a mean of 8 pounds and a standard deviation of 5 pounds. We're going to assume that. And suppose we take random samples of size 25. To find the frequency curve for all those samples of size 25 and their means, the standard deviation is going to be the following. We're going to take the 5 pounds, which is the population standard deviation, and we're going to divide it by the square root of the size of the sample, which is 25. So 5 divided by the square root of 25 is 1, because 5 is equal to the square root of 25. And then we can use the empirical rule to say the following. 68%, again, is the mean plus or minus 1 standard deviation. 1 standard deviation is 1 pound. So 8 minus 1 is 7, 8 plus 1 is 9. 95% chance that we'll have the plus or minus 2 standard deviations from the mean. 2 standard deviations are going to be 2 times 1 is 2 pounds. 8 minus 2 is 6. 8 plus 2 is 10. And 3 standard deviations, we're almost certain that our sample is going to be between 5 and 11 because 3 standard deviations is 3 pounds. 8 minus 3 is 5. 8 plus 3 is 11. Okay. So the answer to the question, what would be our estimated sample mean if we're almost certain? And the answers would be somewhere between 5 and 11 pounds. We're almost certain it's going to be between those two. And if it isn't, if it's far away from those two values, then it falls into question whether the mean of the population is actually 8 pounds. Notice if we increase the sample size from 25 to 100, in other words, fourfold, we increase the sample. Notice the standard deviation is halved, right? 5 divided by square root of 100 is a half of a pound. So now a 68% chance is between 7.5 and 8.5. That's 8 minus a half of a pound is 7.5. 8 plus a half a pound is 8.5, and so forth. Notice that these ranges are now more narrow. Remember, we talked about that at the beginning of class. Sample size increases, the standard deviation decreases, and these range of values become more narrow. That means when the standard deviation is more narrow, that means the sample statistic is a better estimate of the population statistic because it's going to be closer. Look on the previous page. We were almost certain that the sample means between these two values, but now with a bigger sample, it's much narrower, isn't it? It's half as narrow, right? It's half as the distance between these two numbers is half what it was before. So that's the point. Larger samples tend to result in more accurate estimates of population values than do smaller samples. And that's a key point of this, like the entire course, basically. If you remember one thing, remember what's in that little box there, right? If you remember one thing from the whole course, the larger the sample, the more accurate your sample estimate's going to be of the population value. And we just proved it. Now, what are we going to be doing for the rest of the course? We're going to be looking at two possible types of statistics: proportions and means. Proportion would be where we're counting different categories, right? Candidate A versus candidate B. We're going to count how many people like candidate A. So that's a category. We're counting. And then we're dividing the count by the number of people that we asked. That's the proportion. The other thing is we're going to be measuring something like weight loss. And we're going to be calculating the mean of this in our sample. That's all we're going to do for the rest of the course. We're going to either look at proportions or look at means. There's other things in statistics, many more things that we could look at, but that's for more advanced courses. For this course, that's all we're going to look at. Now, we will look at, it is possible, that we may look at two populations and say, all right, I want to know the difference between those two populations in terms of proportions. Well, we could do that also. We will do that. And maybe with means also, two populations, we call them subpopulations, and look at the difference between the means for a particular measurement variable for those two populations. And these are the two techniques that we're going to learn how to do. One is called confidence intervals, which is a way of measuring or estimating the population value from the sample value. It's a range of values. Notice that's what we've been doing, right? We've been estimating using ranges. So we're going to use confidence intervals as a way of estimating the population value. We're going to say it's in between two values, as opposed to saying it's this number, period. Hypothesis testing is the other type of thing, and this is what's used a lot in research. Hypothesis tests, somebody proposes that somebody makes a claim that's different than what most people think about a particular variable. So maybe somebody thinks that a particular candidate, they should be 55% of the people in the population they propose favors candidate A, and then you get some sample and it says 52%. The question is, does your sample contradict that original hypothesis? So we have a counter hypothesis. We say that 55% is incorrect, and we think it's different, or it's greater or less than, something like that. And we use the sample data to try to prove it. So that's called hypothesis testing, and we're going to learn how to do that also. All right, and then this again is an example where you have a poll that shows one thing, and then you have this is an example of hypothesis testing. You have a hypothesis with this committee for the study of the American electorate, say 39% of Americans vote, and then we do a poll of 800 adults, and they found that 56% vote, and then we determine is this 56% reasonable based for this particular poll? Is it reasonable to think this could just be a normal variation around this 39%, or is it highly unlikely? All right, and then through these calculations here, we decide it's very unlikely. So this is, again, what we were talking about before. We'll get into more of this when we talk about hypothesis tests. Again, the last slide here has to do with formulas, for those of you interested in those, which we won't do. The other thing I wanted to look at, let's just unshare this. I want to show you, hopefully it's still open, the textbook. So where are you, textbook? Hopefully, just give me a second here. Let me this here. So let's see if the textbook is still open. No, logged me out. So give me a second. I gotta log back in. One second. Fortunately, Cengage is not the easiest site to get into. All right, back in the game here. There is a part of the chapter that the slides don't cover. I do want to show that to you. There we go. So let me share the screen with this. Now, in the latter part of the chapter, they talk about simulation. Now, obviously, research, once again, I'll just repeat this again. I keep repeating it. Researchers only choose one sample at a time, right? They don't choose multiple samples, but they choose it from a list of possible samples. Now, many times there's not a list out there. So what do? We simulate. We use a computer to simulate all possible samples. We use computers to do that. And oops, right. So I'll show an example. Here's an example here. This is the example I think we were looking at before, where we have a population proportion of 40%, and each sample has 2,400 people that we sample. All right, 2,400 people in each sample. Suppose we asked the computer to simulate 1,000 of these samples, all of which have different sample proportions. And that's what's listed here, by the way, along the bottom here are the sample proportions. So what do they come up with? They came up with the mean of these 1,000. And what is the mean of? The mean of the sample proportions. And the mean of all those proportions is 0.3998. That's pretty close to the 40%, right? Of the 0.4. So the simulation shows that the mean is very close to the mean of the population. Here's the standard deviation that that it comes up with the results here. It doesn't use a formula, it simply does the standard deviation of all 1,000 answers. It comes up with that number there. And then this curve sort of approximates what this histogram looks like. It looks like a bell-shaped curve. That's what typically happens when you do these simulations. You end up with a bell-shaped curve. So this is called simulation, and that's what we're going to be using to do our confidence intervals and hypothesis tests. Now, in a regular statistics course, you would use formulas, and you would use your TI-83 or 84 calculator to come up with these confidence intervals and hypothesis tests. So using formulas. Here, we're going to use computer simulation in this course. Now, each time you do a computer simulation, you'll get different results. In other words, if one person in class does a computer simulation, you're going to get one answer, and somebody else will get another one. So I'm not going to ask you to do a computer simulation as part of a test. I will give you one. You're going to learn how to use the software, but I'll give you one, and your job is to interpret it. Tell me what it means. So, and how are we going to do that? Well, we're not going to use now the textbook uses Minitab computer software, but I'm not going to ask you to get that. It costs some money. So what we're going to use is something free that the math department has found. And let me actually unshare this, and so I'll show you this software. Just give me a second, make sure I see it on here. Here we go. All right. So let me share this with you. All right, and this is called StatKey. StatKey was developed by a family of statisticians. Believe it or not, there is a family of 5 people. They lived together, brought up together. They all decided to become statisticians. So that's why it says by Locke, 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 and Locke, the 5 Locks. It is a family of statisticians, all right? Husband, wife, and children. So they developed this program, and they developed they actually wrote a textbook which uses this. The math department did not decide to use the textbook. They're using the one that we're using, but they decided to use the software that they come up with. Now, how do we find this software on the internet? Just type in StatKey. Type in StatKey and hit enter. And on my browser, the very first thing that comes up is StatKey, and it says Locke 5. That's what you're going to need to look for. Locke 5 homepage. So you just click that, and you get to this page here. All right, so this is the StatKey homepage. Now, I'm going to show you starting next week how to use this, but basically this section in here where it says bootstrap confidence interval, this is the section that you're going to use when we want to use calculate confidence intervals. We're going to go right into here, and the ones that we're going to use is, now CI means confidence intervals, and we're going to use this one where it says single proportion, difference in proportion, difference in means, difference in proportions, and then the first one here, CI for single mean. We're not going to use it for median or standard deviation. So the last one we're going to ignore, where it says slope and correlation. We're not going to do that one. So confidence intervals, we're going to be using this section, And then for hypothesis tests, we're going to be using this section where it says test for single mean, single proportion, difference in means, difference in proportions. Again, the slope and correlation one we're not going to use. And everything else in here, basically, I mean, you can do what you want with this, but we're not going to be using it. All right. So we're going to be using these here instead of using calculators and or doing things by hand. All right. So this is going to make it easier for you. But I've taught this course before. This course, again, is relatively new, by the way. It's only second year. It used to be called elementary statistics, but it's only the second year that it's been taught with this textbook and with this software. So I want to give you a warning. Do not walk in cold in terms of how to use StatKey. All right. In other words, don't think because this is easier than the regular course that you don't need to do anything. You should be familiar with how all of this works, and you should play with it a little bit so that when you see it on the test, it's not a big deal. But it will be a big deal to you if you don't play with it. If you don't do anything with StatKey for the remainder of the semester, that's why I will quiz you on it. Not next Monday, but sometime I will quiz you on it to make sure that you are working on it. Don't fall into that trap, because not only will you do poorly on test number 3, but you will possibly fail the final if you ignore this part of the course. It's not that hard. It's pretty easy to use, but if you're not familiar with it, you will easily confuse yourself. And if you walk in cold to a test or final, you're really, what's the term? Glutton for punishment. That's a term we could use. So I'm giving you that warning. Please do what I ask you to do with this. It's not going to take up a whole lot of time, but it will, if you know what you're doing and you understand it. What we're going to be doing with all of this is not going to be that difficult. So please just follow along. All right. Don't ignore it. Now, one thing I do want to show to you today, and it is something you could play with it if you want, is we've been talking today about these so-called sampling distributions for proportions and means. And it's the frequency curve for a list of all possible samples of a certain size. That's what we're doing. So they do have the ability to do one. Let's say do it for a proportion. I'm just going to click that. And we could create something like what we saw before with the data that we just did, right? That poll. I think there was, what, 2,400 people in our poll. So I'm going to put 2,400 in here for n. That's our sample size. So I'll just click that and just type in 2,400. And by the way, I will, write some things up about how to use StatKey, so that you, once you start using it, you don't need to refer to the notes anymore, but it'll get you started. The proportion I'm going to use is 0.4. I think that's what we used in that example we just did. So we have a population proportion of 0.4. I just click that, and a sample size is 2,400, and I want to generate 1,000 samples. So notice here, there's buttons here for one sample of 1, 10 samples, 100 samples, 1,000 samples. You can click these multiple times, by the way. So I'm just going to click 1,000 samples, and there we go. We've just generated. Now I'm going to click the 2-tail here, by the way. I'll tell you later what that means. But I generated now 1,000 samples. Now there are 1,000 dots on this curve here. Now it looks bell-shaped, doesn't it? And it will look bell-shaped when you do many of these samples. Each of these dots represents a sample of size 2,400. Now the mean of all of these samples of all these proportions is 0.4. Right? It is 0.4. And the standard deviation of all 2,400 of these sample proportions is 0.01. Okay. Now, when I did 2-tail here, I was basically wanting 95% of these 1,000 samples to be in between two values. All right. So the two values in this case are 0.38 and 0.41. There are, if you see the colors here, 95% of these dots are between these two values. They're the black dots here. So 95% of 1,000 samples, that's 950 of these samples have sample proportions between 0.38 and 0.419. That's how to read this. That means 5% are outside that range. 2.5% to the right, that's the red dots over here, and 2.5% on the left. What's 2.5%? 1,000, that's 250. Not 250. Sorry. 2.5. Did I say 25%? I meant 2.5%. 2.5% to the right, that's 25 dots. 2.5% on the left, that's 25 dots. All right? That makes up 100% here, right? 2.5 plus 95 plus 2.5 is 100%. All right? And in the middle here, where that arrow here, that's 0.4, that's your mean. And what's really cool about stat plot is that you can point to any of these dots. I'll point to this one right here. And on the right here, it gives you the sample, that the sample count is there. It gives you the proportion for that sample. For that particular dot, the count of the number of people out of 2,400 who, I guess for candidate A, whatever it was for, I forget what it was for, 987 of those 2,400 said yes, or whatever the question was, and then that's 41.4%, 0.411. I could pick one down here. Let's pick this one here. Count is 925 out of 2,400. That's a proportion of 0.385. That's 38.5%. Any of the ones down here? Here's a red one down here. 894 is the count out of 2,400, 0.373, and then one up here, like this one here, is 1,028 divided by 2,400. That's 0.428. I could ask you anything about this curve here, right? I could ask you, what is out of these 1,000 samples, what is the biggest proportion? You just run your, it's this one right here, right? 0.43 is your biggest proportion. What's your smallest proportion? One down here, 0.37. All right, so that's how you use StatKey. All right, in terms of generating a sample proportion, and we could do the same thing with the mean. We could generate a sample size, I don't know, 200. Making it up. All right, samples of size 200. Now, they do have samples in here with different means in them. But here's one. Here's a population of 82 individual values with a mean of 53.537. Has something to do with grad schools. I don't know exactly what it's referring to. And here's the standard deviation of the population, 36.89. All right. So here it actually shows you the population values here. And then you can generate random samples of size. Again, I'm going to make them size 200. I don't know. There we go. Oh, you know what? It's not allowing me to do that because there's only 82 in the population. So I'm going to say size 10 or 5. Let's make it size 5. Sample size of 5. Obviously, it can't have a sample size 200. There's only 82 in the sample. All right, so we're going to have 5 of these grad schools that are in our samples, and we're going to generate 1,000 of these. All right, there we go. Again, bell-shaped. This is again a sampling distribution. And each of these dots represents a sample of size 5. And it's measuring the same thing, whatever the population's measuring. It's just taking 5 out of those 82. Each one of these is 5 out of those 82 members of the population. So this one here, I just put my finger over, has a mean of 52.2. Notice there's only 5 dots on that down here. See it, 5 dots. I can run my finger over here, and this is minus 73. There's a mean of 102.6 up to the 5. All right, so I want you to get used to it. You can go in here and just play around. Just play around. There's nothing, you're not going to harm anything by playing. All right, just get used to doing this. So these are sampling distributions. These are simulations. The computer uses what are called algorithms to come up with these simulations. There's nothing that you need to do except just to run it. Pretty easy. All right, and then by the way, if you want something other than 1,000 samples, let's say you wanted 2,253 samples, then I just do another 1,000, 2,200. You click this twice. What did I say? 53, 2,253. 1, 2, 3, 4, 5, and then click this button 3 times. I have 2,253 samples. Okay, so pretty easy to do. All right. I want to show you one more thing before you leave today, so that you also can play around a little bit. If you click this up here where it says statistics, this unlocking the power of data, if you click it, they are obviously trying to get you to buy the textbook. Don't buy it. You don't need to buy it for this course. It's not part of the course. Here are the Locks, by the way. There they are. The family, the Lock family, like the Von Trapp family. This is the Lock family. And then along the side here are different resources that you can use. If you are into reading, you can look at the PDFs, but I'm sure many of you don't want to do that. But they do have videos, which is nice. So if you click videos, they do have different things places they spoke at, and you can look at any of these videos, by the way. But the ones that I would recommend at first are the introductory videos. And there's one too that's called Introduction to StatKey. It's by one of the children, I believe. I don't know if Robin is a children or a parent, but it's 21 minutes long. Just click it and watch on your computer, and it will give you an introduction to how to maneuver around StatKey. All right. Once we start confidence intervals, I would recommend clicking this one, overview of Bootstrap confidence intervals, where they go through how they come up with the confidence intervals. And then when we go to hypothesis tests, there's a video for that too. We call them randomization tests in here. All right. So if I were you, play around in StatKey, watch the introduction to StatKey. It's only going to take you 21 minutes. And that way, when we get to class, you're not going to be totally unfamiliar with it. And you'll be able to use it and interpret it. All right, that's the whole idea. All right, so that is all I have for today. Are there any questions? Any questions at all? Stop sharing. No questions? Okay. So remember, there's going to be a quiz on Monday. It will cover chapters 17 and 19 in the textbook. It will not cover StatKey, but StatKey will be covered in future quizzes. So please don't ignore StatKey. Again, I've repeated that several times. So if you don't have any questions, I will stop the recording.